Thank you, Edwin. Well, I will talk about a tool that we are developing together with these people. And it is in development yet, but we have very good results, I think. So what is the idea or the main motivation to develop this tool? Well, I think we really wanted to bring the latest data releases from Virtual Observatory into this DOM. And we are working on that so people can make shows with the latest data. But unfortunately, it is not straightforward. There are several steps that we have to do before. So the first one is, well, we have to download the data, then we have to transform the data, and finally we have to set up or configure the software in the DOM to create nice visualizations. So for the first step to download the data, we can do basically in two ways. The first way is to visit a web portal, select the data, create the queries, and well, download the data in a particular format. The other way is by using APIs. And in this way, you should be able to write scripts and use particular packages like AstroQuery, CashJobs, or PyVO. But in this case, you have to write your own script. So nothing is wrong with this. So everything is fine, but it is time consuming. So for the next step, we have to transform the current variables as they are in the catalogs. So we have different variables, and then we have, but unfortunately for DOMs or for the software of the DOMs, we have to use another kinds of coordinates. So in this case, for example, in astronomical catalogs, we have RA and egg, but software in the DOM, we need galactic coordinates like X, Y, and Z. So we have to perform this transformation, and we have to write scripts. As far as I know, we don't have any tool that can do this transformation automatically. So as I mentioned before, nothing is wrong with this, but unfortunately, it is very time consuming. It takes a lot of time and is prone to errors. And then you have to write a script for every data set you download. And I can tell you that it is very, very time consuming and prone to errors. So the main goal or main aim is to really accelerate and to create a tool that can be useful for people who create presentations and accelerate this process. And at the same time, we really want to exploit the data that is in the virtual observatory because, well, it's there, and then I think this can be used for scientific purposes as well. So we are proposing and we are developing a very simple tool. So this is the basic architecture. We create a graphical user interface, develop a class or a controller that can be can establish the connection to different catalogs like Gaia catalog or ESO or the KITS catalog, so other different catalogs. So far, we have implemented connections, or we are able to download data from SDSS, for example, from Gaia and from ESO. I will talk more about that later. And then, well, apart from the controller, we have a module that transforms the data into DOM formats. And for every download, we have created, well, not for every download. Each time we download a particular file or data set and perform a conversion, we store all the metadata into a small data set. So that's the idea. And then we have developed this interface. So this is a very simple interface. Let me see if I can point it here. I can use the pointer here. No, sorry, I did something different. Okay, I think I can use the mouse. So I will explain very quickly. So on this, oh, you cannot see the pointer. Great. Okay. On the left side, on the top left side, you have a combo. Which one? Ah, okay. Oh, thank you, Rees. Okay. Yes. Here we have a combo where we have all the different catalogs that we can query. Once we have selected the catalog, we will see all the tables that are in the database. And once we select a table in the database, in this panel will be displayed all the variables that exist or columns that exist in the table. And then we can select the variables that we need interactively. And each time we select a variable in this panel, we will be added, and we can apply some filter. If we make a mistake, we can delete the variable or that we don't need it. Then we have this button ADQL that prepares a very basic ADQL script, and then we can download and save the file. At the bottom, you can see some metadata, like the date you perform the query and the execution time. So that's the first step, download the data. And then to transform the data, we have created another small interface. In this case, in this example, we transformed the downloaded data into a spec file. And the software at the DOM requires some X, Y, and Z coordinates, like speeds on X, Y, and Z, color, and absolute magnitude. So on each of these panels, we have the variables that are used to create the required variables at the DOM, so we can just select them. Well, the software tries to guess the appropriate variable. If it is not correct, then the user can just select the appropriate variable from this combo box. Then, yeah, we can just convert and save the transformation. And yeah, finally, you will get a spec file, and then it can be installed in at the DOM. Then, we have performed some experiments, and we have downloaded some data from different catalogs. So this table, in this table, we don't want, the purpose is not to compare the performance and speed of the download from the dataset, because the conditions are very, very different. Some sources or some astronomical databases have different constraints, and then it is very difficult to really compare. So the purpose of this table is just to give you an idea of the amount of time that it will take you to download some amount of data. So for example, from the kids catalog, this data set was downloaded from ESO, and we downloaded 10 million records, and the time was 1.78 minutes approximately. Then we have downloaded some other data sets, like from the SDSS. The biggest one was this one, approximately 185 million rows, which is in size of about 11.5 gigabytes. And unfortunately, well, I don't know if this is unfortunate, but maybe fortunately, we succeeded downloading this data set, and it took about 16 hours. The other one is from Gaia, and then we have downloaded 145 million rows, about 11 gigabytes, and it took about 4.15 hours, more or less. So some examples of visualizations. These are just static visualizations, but Rees will show you an animation about what we have downloaded. So this is just a screenshot of some data downloaded from SDSS, about 13 million objects. This is another visualization from the Gaia catalog, 19 million objects. These objects are smaller than 1,000 parsecs. Sorry, the distance to these objects are smaller than 1,000 parsecs. And so we have some conclusions, but after that, Rees will give additional information about some other data sets that we have downloaded from Euclid. So the first conclusion that I have, well, first we have developed Tomcat, and we think that it is a promising tool to bring data into the DOM. Well, downloading can be still time consuming because we depend on many different variables: the speed of the read, the speed of the network, how busy is the server, the speed of the connections. I don't know. We have many different variables, and then unfortunately this can be time consuming. We have done a pre-release of the software. It's in this. It's in a web. It is in a web repository. The software works for. So far, we have tested the software on the Linux, Mac, and Windows. We still have to improve it. It's not a final release, so it's still work in progress, but can be tested. If you want, you can download it and test it. And I think that's all. Oh, okay, well, we have some future work. So we have to, the idea was to prepare the final release this month, but we will not make it, unfortunately. So we have released, we will release binaries for Linux, Mac, and Windows. We would like to support concurrent downloads. So far, we can support only one download at a time. We have downloaded the data from Euclid, but it is not yet embedded in the software. And now I will give the floor to Rees.
Thank you. Okay, well, we thought as it was there was so much Euclid presentations here, it would actually nice to have a demonstration of using this to convert some Euclid data. Well, obviously simulations of Euclid data. So we chose to select data from the so-called Euclid Flagship 2 simulation, which is a simulation involving 2 trillion dark matter particles, 2 billion galaxies. Now, the first thing to realize is that if you put in 2 billion galaxies into any planetarium system in the world, you will break it. So you have to sub-select the data you need. And that's why it's increasingly important to have a tool like this, where you can select data easily. So what I chose to do for this was to select nearby galaxies. So these are all with a redshift cut of 0.03, so within 100 megaparsecs. Because I know from working in this dome that actually that's quite pretty data. Now this is where I'm using OpenSpace for looking at this, which is what Edwin mentioned. We'll go into the full dome in a minute. But OpenSpace has the advantage, it's very easy once you've created these data sets to read them in and then just play with them straight away. So I'll just, it's a small visualize. Yeah, this is now pulling away from the sun. And you'll see it's an empty universe because I've only put the Euclid simulations in it, so only galaxies. So now we start seeing the first nearby galaxies. And then very soon you'll start to see the structure. And then we'll just move around this a little bit, just to show you roughly what you can, the capacities of OpenSpace are actually very similar in many ways to the system that we're using here. Here I've got the fact it's easy to bring it into OpenSpace, the data, but the OpenSpace still doesn't work properly in this dome. We've got it installed, we can switch it on, I can display data sets, but there's still some distortions that we need to sort out. Okay, so now I want to go on over to the full dome demonstration. Okay, now, what I'd meant to do at this stage is ask them to take us out to the Euclid, the same data that I was showing there. But here in rehearsals, we discovered that there was a problem when we read in this data set. There's nothing wrong with the data set, but the integration of the data hasn't worked. So I can't show it to you. So unfortunately, what I'm going to do is take you to the existing data that we have in this system at the same location. So the same redshift cut, but something like about 100 megaparsecs. So you'll see what it will look like when I get it working. But this shows that we still have quite some work to do with this system. I mean, the production of the spec file is fine, but if we're carrying on using it with this, we've got in touch with the manufacturers of the dome, and they're working with us. And they've already sent us some brief software which they offer to embed in the system. And we hope that in next month, this is all fixed. Now you can see here the colors are rather different from the one that I displayed, because I was just using an astronomical color, which I just defined. Here, they're actually using a false color just to identify different populations. But that's very easy. That's just something you just set up in the configuration file, but it's a configuration file of the planetarium. So that is something that we cannot do in this tool. You will still have to have a knowledge of how your local planetarium software works to alter the appearance like this. I must admit, this is one of my favorite data sets actually inside the inside this dome. I find it very, very attractive. We're not doing it today because it's difficult technically to put glasses out, but in 3D, which this dome is capable of, this is even more beautiful. Okay.
Make it more dramatic.
In the shows, we certainly do. Okay, I think that's fine. If we can now go out a little bit further, please, or a lot further, in fact, because that, as I said, was redshifts of inside 0.03. Now we're now going to go right out to redshifts beyond 1.3. And I almost put this in for historical reasons, because this is the first ever data set we brought into the dome. So you'll see this has got no color because we were learning how to use it. So we just ignored the color, we ignored the luminosity, and we just put a white spot where there was a point. And this is the kids data release 3. And it was done with just a series of scripts, which we've now put into DomeCat. But this work actually was one of the reasons we decided we needed DomeCat, because this took me ages, together with the help from Venus. And also, you can see that there's something very funny. Okay, you can see here the individual observations that make the thing up. So that's why they're squares. Each of these squares is an individual observation. This is from kids, I should have said, which is one of our pride and joys in Groningen. But the other thing you might notice, there you can see it. There's almost a plate structure in there. It's not continuous. You get the beams from the observations and then these lines. And when we saw these, our first thought is, we're not doing this conversion properly. We're doing something wrong. And we spent ages tracking this down and finally convinced ourselves, no, that was an artifact in the data, that there was something funny with the data release 3. And at that stage, data release 4 was about to come out. We put that in and the artifact just totally went. So in fact, but then we realized that we really had to have a system that we could do this automatically and not continuously have to look and chase up issues. There you can see the nature then again of the observations, looking straight down them there. So this is a block of observations. This one is just an individual one. The pattern looks funny because data release 3 was very, very incomplete. So there's some areas in the sky which are totally covered and some like that where you just get one observation. Why there's a hole in the middle, as I said, I cut it at a redshift of 1.3, which again, you have to put some cuts in. If you can't, even with the size of kids, which is tiny compared to Euclid, you can't put the whole data set in. And anyway, after that little fly through the universe, because I just wanted to show you at least something in the dome, and that's the end of my talk.